Anyway, I'm Tom Friend. My company has me alternately listed as Toshiba, was it Toshiba America Electronic Components, but our new name is soon to be Toshiba Memory Corporation or Toshiba Memory America. It's the same people. And no, I don't know what they're going to be changing it to or who's going to buy us. You know as much as I do. So the interest here today is in how to tweak the maximum kinds of performance bits and corners in NVMe. And this came from my own background as a systems coder for a lot of years. And so there's no set standard that says do all of these steps in this order and everything will be gracious. Here's lots of little tips that I've learned along the way, and any of you who have run into similar issues, feel free to, holler or tell me I'm full of crap as you see fit. So to begin with, you need the right attitude, and it's all about the details. You see something in the very beginning that doesn't make sense. Don't worry about your boss telling you you've got to have so much tested by the end of the day. If it doesn't make sense to you, find and figure out that issue first. Sometimes it's those little things that will come back later. So if all else fails, at least write them all down so that you have a chance to come back to them later. I just usually, I'm of this very logical, hey, wait a minute, why is it breaking up my packets into 128 byte chunks? I thought I was getting 4K transfers. What's going on here? So I would investigate that. I would spend a lot of time on that until I understood what was going on. Somebody else may decide to tackle that problem later. Anyway, some of the tools you need. You need an analyzer. PCI Express analyzer is really the only way to do this stuff. If you've done storage stacks before, you know just how valuable it is to have a SAS or SCSI or SATA analyzer when you're dealing with file systems. And whether you're developing a file system stack or whether you're developing a device itself, all the same things apply. In this case, it's PCIe, which is the wire protocol for NVMe devices. The smartest and most useful of the new PCIe devices will actually decode the NVMe streams for you and tell you when you've got it right or not. And those can actually be very handy as well. But since I don't work for any of those companies, I don't have that information readily available to you. Kernel level debuggers, if you're working, drivers will come in two different models. You'll have the user level model, which is in Intel's SPDK, or the standard kernel level driver, which you'd find inside Windows or in the Linux kernel. For any of those, you really want a kernel level debugger. Even in the user model, you still have some kernel functions you need to step into occasionally. The test system that you're developing your NVMe widget or stack on works a whole lot better if it has a really functional file system at the same time. So to have a file system where you can be running a real Linux kernel is quite helpful. So you want to have a SATA device, SATA or SAS kind of stack on there to run a real Linux kernel off of at the same time that you're running the test debugging things. And Never count on the file system. A paper notebook is probably your best friend. I have stacks of little hardbound notebooks going back many years with lots and lots of cryptic notes in them, and they never blue screen. They're always there. Among the interesting tools, PCI gets in your way. So the first thing you need to know about is a handy little tool called LSPCI that will give you all the gory little hidden details of every last bit of what's going on down in PCI Express. So you go to enumerate one particular device, and you come all the way down through, and one of those nasty little things says max payload 128 bytes. And that's the key that allows you to realize that no matter how you set up your NVMe device and tell it you want to do 4K transfers, PCIe underneath is going to break it up into 128 byte transfers, because that's the size of the memory blocks in the switch, the PCI switch. And they do this because this is a way they can maintain simultaneous fabric-style connections inside the switch, so that they're non-blocking with one another. More memory means more expense. So while you might expect to find this inside a laptop or low-end desktop machine, on a high-end server box, you will find 4K as your max memory size. So those are the kinds of systems that probably be better for you to start with, certainly when you're doing benchmarking. And along the way, you'll want to be able to test. So even if you do get that really super high-end system that gives you the nice 4K switching block size, you want to be able to set it down to 2K, 1K, 512, down as small as possible, just to make certain your device, if, like me, you're working for a device vendor, that it all works correctly. And it's usually good to do that in the beginning, and when you're first doing device bring up, because that's all the real bottom end sort of stuff. Now, before you ever get into dealing with things like setting up submission queues, dropping a command on the submission queue, watching it appear on the completion queue, you want to be able to do just simple things first. Read and write the registers. Can you do that at all these different settings? But that's just some of the magic of doing bring-ups. For silicon bring-up. There's another tool called SmartCTL, or it comes from Smart Tools, smartmontools.org. And this gives you the information you want for what your NVMe device reports itself as. And it's just another command line thing. And all it does is just does an identify controller. It'll do it does an identify controller and identify namespaces and prints those out for you. So if you want to see if your device is working right, and then plug somebody else's device in and see what theirs reports, you have those comparative things, and it gives you all those odd, arcane little details that only matter to those of us who really get into those little details of how to report your power states and odd little things like that. So gathering up all these different command line tools becomes a very worthwhile thing to do. Another one is the classic NVMe CLI. It's actually it's a Linux tool set, and it's actually just NVMe when you actually type out the commands. And it is probably one of the most useful debug tools that you'll yeah. Yep. Yeah, and you'll send down one command, you'll watch it come across on the PCI analyzer, and you'll scratch your head, what? And go back and do it again, and yeah, it still came out wrong. And then after you've stepped back through your own firmware and you realize, oh yeah, I byte swapped those 3 fields. And that's why the analyzer didn't understand it. So it becomes a very critical tool when you go through and start testing your firmware on a command-by-command basis. As you test out all the different bit fields in your commands to see which ones work correctly, which ones have the fields backwards or off by 1, or all the other little classic bugs and quirks that you end up with. I'll mention briefly about fast path versus slow path. In most modern storage controllers, there will be a fast path where all the commands that are truly to be optimized as quick as possible are not run in firmware at all. But they're taken over by a separate automation engine inside the chip. And they run without any help or backing from an ARM processor on board. They just have their own separate engine. And they will read through the submission queue themselves in many cases and execute directly and drop things in the normal path right onto the completion queue. So the ways that you test and debug those things I'll describe briefly, but pretty much what I've said already. But other than that, the real effort is in testing those odd little vendor-specific commands, and the ones that are not in the normal fast path, things like getting logs, namespace management, those sorts of things, where you might as well just do it in firmware just because. And you have the flexibility. And other reasons for designing to use the slow path may include portions of the spec where you see a lot of churn happening between 1.1, 1.2, 1.2.1, 1.3, ECN1, ECN, yeah. So as you see a lot of changes in parts of the spec, you may decide you want to keep things in firmware, not necessarily move them into the fast path. Time. We all want to make certain that each and every command that we do runs as fast as possible. And in the ideal world, every fast command should be able to stack up itself and will go to a depth of 32K, and everything will continue to work wonderfully. The problem is the media that all these NVMe drives run on needs some maintenance time to deal with their own issues. Long ago we had this thing called spinning rust, and we all knew, well, many of us knew and loved all the different maintenance things you would have to do to that odd little spinning piece of rusty glass in order to keep it running. Well, we have the same sorts of issues that happen inside NAND flash. And in the future, we're probably going to see all kinds of little quirky things that happen as we move to storage class memories, whether it's Optane or STM RAMs, RRAMs. They're all going to have their own specific little quirks. And so for NAND, we have things like read disturb. We have write disturb. There's times where we need to rebuild a set of clean erase blocks. There's times where our dirty block pool is getting too big and we need to knock that down. So if you're working on a storage stack, it's nice to be able to alert the devices that I'm going into an idle state for a while, so that the device has time to rebuild itself when you don't care. So that's the other side of time, is if you're a host, let the device know when you don't need it, because it'll be a lot more responsive for you when you do. Those of you who were here for the Flash Memory Summit, anybody? There's this, yeah. Well, you didn't get to see this really cool demo, but it won Best of Show anyway, because the judges got to go around to all the booths inside the night before the fire, and they got to see all the demos that none of the rest of us did. Well, one from my company won the Best of Show. And this was for a demonstration of what was called I/O determinism, which is one of the big new things that's been discussed a lot in the NVMe technical group. This is probably the single biggest change in device driver ideas in a long, long time. Just the simple basic idea that a specification will tell the host what to do. Whereas for years it's been, no, you can't tell the host what to do. The host tells the device what to do. And so in the specification, we can never say anything about host shall, and we can't even say host should. But when they broke that basic premise for I/O determinism, it boosted the performance by a 10x. Not 2, 10. That was significant. But the real thing that they went and worked on was giving the device time to be able to do that media maintenance in the background. So even if you're not going to go to the level of complexity of implementing an I/O determinism device or stack, find ways to divide up your time, to give your devices underneath that chance to do the media maintenance, because it'll pay off for you when you do need that extra performance time from them. Now, the basic NVMe queuing structure works very well for most installations. You can have 64K different queues. Actually, it's actually maximum of 16K if you're using the weighted round robin, if I remember right, because you've got the 4 separate queues within each of those, right? So, but in either case, the idea of having separate queues on the thing for every separate processor core works great up to a point. But when you've got 10,000, when you're dealing with a very large data center type of installation where you may have 10K, 10,000 drives, and at least that many cores, think about the amount of memory that it takes just to deal with that. And so there's some ideas coming now into the NVMe group asking us to rethink about the possibility of instead just having one queue per core, per controller. And the actual I/O priority would then be inserted into each of the commands instead of being insinuated by which queue you drop the command onto. So it's coming. There's one particular customer who's really pushing for it right now. And it may be of greater interest in the supercomputing market, where having very high bandwidth to a large amount of storage has a lot of uses. As far as developing firmware, one of the key features that we added in the 1.3 release was telemetry. The idea of telemetry is it allows the device vendors, the storage device vendors, to report back only to themselves any information about what happens inside the devices. What would you want to know? Well, I spent a lot of years at Microsoft working on the crash debug system inside Windows. That wonderful thing that would, in the early days, just lock up your machine for 15 minutes as it would gather all the information off of your machine to pack it up and send off to Microsoft and explain why you got that blue screen. It got better over the years. And the reason it got better is because they were able to get this information back about why Windows was failing. And they did a statistical analysis. They still do, every single day. Which bugs are causing users the most pain? And those are the ones that they fix first. With this system, you can do the same thing in your own firmware. Because if you have a small bit of a debug stack inside your device, so that every time that ARM crashes, you report back why. You save it away on some of the flash inside. Save away what you need to know to fix that problem. Save your stack, save the register context, put it all into a block somewhere. So that at a later point, telemetry will let you extract that out of the machine. And those places where you ran into a null pointer, where you got a divide by zero, where you just hit a bit test that you were not expecting, where you got an assert. Oops, I forgot and left that in my production code. No, we've never done that. Having those features in there in telemetry allows you to fix those bugs and fix them on a much better schedule, much more consistently. So that is truly, at least in my mind anyway, one of the most important aspects of the new features that we've added in 1.3. But that's my own background, so that's my take on that. And now I've killed all my time, and I'm done early. Any questions? Any comments? It was as I feared. You guys got your ice cream, you went into a carbo coma? It was the cobbler? Is that what did it? Well, it lit me up and it puts you guys out. No, I've spent a lot of years bouncing back and forth between silicon bring up and firmware, and years doing device stack work, and so I've seen many different layers up and down in the stack, and all the same tools, the same processes apply, no matter where you fit into that picture. You're just looking at the slightly different details of it. If you're working on the OS stack, you're far more focused on what kernel resources do you have open? How many locks have you got outstanding right now? It's issues like that that you really care about. How many locks have you got on this one particular memory block right now? Becomes something you're really going to stress and focus on at some point in your day. But if you're doing silicon bring up, it's like, my God, how do I understand whether it's breathing or not? Well, it's drawing power. We think we loaded the debug code in, and the LED is blinking that says it's alive. And so you have to start stepping through with the PCIe analyzer. Do simple reads. Does it respond? If it doesn't, why not? Then spend your time looking back at your source code as you go through that read register routine inside, depending on how your hardware is designed. Firmware will have similar issues.
Is there any pushback on telemetrics that you're invading privacy?
The interesting thing about telemetrics is it's your information. You can feel free to encrypt it any way you want because it's coming to you. Okay? And I don't know how it's done in the Linux stack, but in the Windows stack, there are certain classes of Windows crashes where the crash dump will automatically assume that a problem occurred in the storage device. One of those is if the device took too long responding to a page read request. That's like a really fatal thing to do. And so it'll reset the device, save away that context, write it out. But at the same time, it will also try to gather telemetry logs out of the device and include that with the Windows crash dump. If you have registered your company, your vendor company with Microsoft, you will have access to all of your own little dumps that come from those conditions. You're the only one who gets them. Microsoft won't send them to anyone else. They'll only come to you. That happens through the Windows Developer portal. You get signed up through that, just the way any software developer can sign up to get crash dumps for their calculator program or whatever they have. But in terms of user level privacy, if you're going to send things from your device, please don't include any user data. I know. You think you're not, you want to make certain you're not. That's a very bad thing. Anything personally identifiable is a very bad thing. And really, it was put in there so that we can fix our own bugs. There's actually two different classes of requests in NVMe. There's the host initiated, and then there's the device initiated. The host initiated one says, hey, I want you to take a snapshot of where you're at right now and send it to me. And that's the one that Windows will request when you've gone and hung the paging mechanism. But one of the little subfields in there says, I've also got some of my own device initiator data. And so then you have, and so that would allow the host to then request a client initiated data log. And that's where you can keep all those records of when you restarted your firmware because it wrapped off the end of a buffer, because you AV'd for all those different software reasons that you decided you had to reset the ARM and start over again. Keep a list of those stack traces, and you'll get that opportunity to send them back to yourself. A very handy thing, and to develop your own little log snarfer to use in your burn-in labs. Customer qual labs is another great place. You know, when it dies out there and the customer says, oh, I don't know, you may have that information right there if you had that log gathering mechanism there.
Could you speak to the performance improvement that you guys were able to deliver at the Flash Memory Summit? What exactly did you change in terms of the idle state detection?
Everything. Okay. The idea is that the controller is going to be either in a state of writing or a state of maintenance. And mostly they're writes, occasionally they're reads. But that was the full bandwidth deterministic window. And then there's the time that the device is given to do media maintenance, where it could do its read patrols, where it could deal with fixing up its erase block stacks, all those other little maintenance things that need to be done so that when it goes back into its next deterministic cycle, it's got everything in place. Maximum number of available erase blocks ready to go. You're not going to run into any weird read problems because the patrols have been done. All those kinds of nice things happened already. And so those little unexpected things that we normally have to throw into our code to deal with, oh, wait a minute. I can't do your write request right now because I got to go do this other thing. That goes away. And it really did an effective job of solving the issue of tail latency, which is what it was really all about. You know, the idea that SSDs will respond in milliseconds. Yeah, it's true. 90% of the time. But there's this really long tail. And there can be some times where your SSD will respond in 2 or 3 minutes. The way these hyperscaler guys orient their code, the way that they do all their database accesses to build a page for that Facebook page. Think about the number of database accesses for every little message, every advert, everything you see on the screen. Every object there will take at least 3 different database, i.e. disk storage accesses. That's thousands. And they all happen serially. They're not in parallel. So they have to happen very quickly. And the same thing happens for Amazon, for the same reasons. You go to look at your shopping cart or you want to go watch a video, there's hundreds of database accesses behind creating that page that you want to see instantly. And if you don't see it instantly, you might not buy. Or you might get PO'd at Facebook and say, oh, it's crap. It just doesn't work well for me. It's my lousy ISP or whatever. It's the hotel Wi-Fi. It may not be the hotel Wi-Fi. It may be some SSD got hung up inside their data center and they wanted to keep that from happening. So they wanted an absolute consistency. And that long tail of latency they wanted to bring in, and this did it. in a very phenomenal manner. Other questions, or? Well, just as a show of hands, how many are actually device-focused people in here? How many working on host stacks? How many in the middle? Arrays? Okay. Yeah, all right. Yeah, you guys have got a special set of challenges. Yeah. That's yeah, it's a big challenge just to get the timing right between all those devices. Orchestrate them all to work cleanly together. Yeah. Anyway, thank you all very much.